We're covering the Python notebook that accompanies Chapter 4 of the textbook Mining Complex Network. So this chapter is concerned with the notion of degree correlation. So we're going to explore various notions of assortativity, disassortativity, for example, and some measures of assortativity. So in a nutshell, the notion of assortativity corresponds to the tendency of nodes of similar degree to form edges between them. So do high degree node tend to link to high degree node, low degree node to low degree node? That would make up an assortative network. And then the opposite. Maybe we have a tendency that low degree node tend to link to high degree node, and that would be disassortativity. That would be disassortative or negative assortativity. Okay, so first things first, let's point to the proper directory and load the packages that we're going to need. We have a number of functions that are defined in the next cell, essentially computing the different measures that are fully described in the book in section 4.3. So let's quickly go through those. Degree correlation is this function KNNL, which is a function of the degree with respect to the degree of the neighboring nodes given nodes of degree L. And the same for directed graph. But for directed graph, there are four different flavors because you can consider in and out degree respectively for the source and target nodes. So there's four different mix if you want. And then the same, the computing the value of degree correlation given a degree distribution, but for a neutral graph. This is useful for comparison. Then we have a function to compute the correlation exponent via linear regression. Again, the details are given in the book. The Rich Club coefficient, again, given in the book. Is there a group of nodes of high degree that tend to link to each other? So we'll give an example of that. And then basic function to compute degree assortativity. So in the case of undirected graph, this is the same as the iGraph function. In the case of directed graph, we kind of wrote this function because the iGraph version only specify one specific mix for the in and out degree, while we want to be able to explore all four different combinations for the in and out degree. Okay, so let's run this and have our functions ready. And first, we're going to be looking at two families of random graph, namely the random geometric graph that we saw already in a previous chapter, which is parameterized by this radius value that indicates the propensity of creating an edge at a certain with nodes at a certain distance from where we land on the torus. So if you have higher radius, you will create, of course, more edges. And then the uniform or Erdős-Rényi graph. So we're going to be generating a bunch of graph with 1,000 nodes, varying the radius for the random geometric graph. And then we're also going to generate a uniform graph with the same number of edges as the corresponding random geometric graph. Okay, so the code is given here. We're looping through the value for the radius, computing the random geometric graph, the Erdős-Rényi graph, and then for both cases computing the assortativity, storing those into a data frame. So we're storing the assortativity for the two types of graph and the corresponding average degree, and then plotting. So you can clearly see that for the uniform graph, assortativity is essentially zero, while the assortativity is positive and relatively high for the random geometric graph. And you can imagine that this would be the case because if you remember the plot that we had of a random geometric graph in an earlier chapter, you have some clumps, some areas of the torus where there's a lot of node tend to cluster. So you will have lots of high degree node connecting to high degree nodes, for example, creating positive assortativity. As the average degree gets higher and higher, well, every node will have essentially the same or very similar degree. So now the assortativity is going to be more like a neutral graph, which we're going to see in more details here, where we're actually going to plot the degree correlation function KNNL for two of the cases that we saw earlier. So a relatively small radius, let's run it. So we're generating the graph and basically plotting the distribution of the degree correlation function as a function of the degree. And you can clearly see the positive correlation in the case of random geometric graph, while for the Erdős-Rényi, the correlation is more or less equal to 0 in this case. The dashed line correspond to the KNNL hat, which is the value you would get for a neutral graph given this degree distribution. And if we do the same for higher value for the radius, then for the random geometric graph, you can see that, well, okay, there's still some slight positive correlation, but more or less all the nodes have extremely high degree. So you're much closer to, a sortativity equal to 0. And of course, the same for the Erdős-Rényi or uniform random graph. Okay, so the random geometric graph does not have like power law degree distribution, for example. So this is why we can consider another type of model, which is called a spatial preferential attachment. Again, all the details are given in the book. We're just going to quickly browse through it and saying that in these kind of this is going to generate a directed graph. So you start with a single node, and at a given step or time t equals 1. And then at every other step, you're going to generate a new node, which you're going to randomly place on the square. For each of the nodes that are already in the graph, we're going to connect with a directed edge. So VT is the new node created at time t. We're going to make a connection or create an edge, a directed edge from VT to U with probability P if VT is in what we call the sphere of influence of node U. Okay, and the sphere of influence is parameterized by the nodes in degree at the time t. There are two other parameters also, A1 and A2, details in the book, but one of the interesting facts for this model is that there are some theoretical results for the in-degree power law distribution. So the exponent is theoretically given by this value here, and then the expected average degree is average out degree, is given by this value. So we're going to verify those two results or those two equations. Okay, so this is simple code to generate this spatial preferential attachment given the parameters, and we're generating a graph here with 3,000 nodes. That takes a few seconds, so let me run this also so we can have everything together. So in the second cell, we're just going to plot the graph. I'm going to ignore remember, we're considering the torus distance here. So edges would kind of wrap around and create a graph that is not very nice visually. So I'm just ignoring those edges for the sake of plotting. Okay, so we've generated a graph. 3,000 nodes, 16,825 edges. This is what it looks like. So it kind of looks like the random geometric graph we saw earlier. But remember, we now have a directed graph, and we're going to have a power law distribution for the in degree. So those are the functions that we had defined earlier to compute the sortativity. So in this case, we're computing here the directed assortativity for the different mixtures. So it could be M1 could be in degree or out degree, and M2, the destination node, could be in degree or out degree. So source and target, we're considering all pairs of nodes that form an edge, and we're considering respectively the in or out degree for the source and the in or out degree for the target. So 4 different cases. We can also consider assortativity if we consider by neglecting the directionality, so just undirected assortativity. This is just comparing with the function provided by iGraph, and then we're also looking at the average out degree and comparing with the theoretical value that we saw earlier. Okay, so those are reported in the book, but in short, what we can see is that there's a relatively strong positive assortativity for the in type and for the out type, and the same for the correlation exponent. So positive indicates positive assortativity for both of those values, while the values are slightly negative for the in-out mix. Okay. And we can check the iGraph function. So for iGraph, the undirected assortativity minus 12 is the same as what we obtain with the function that we have. Makes sense. But for the directed assortativity, if you call the iGraph function, and that's the main thing I wanted to point out here, is the only value we'll get corresponds to this out in type. So from to node, you consider the out degree of the from and the in degree of the to node, which one may argue is the natural, directed assortativity, but we can really consider the other ones also. And this is verifying this average out degree of a graph that we've generated and comparing it with the theoretical value. So even if we don't have that huge of a graph, we can see that we get the similar value to the predicted or the expected average out degree. And the same for the power law exponent for the in degree. So we already saw how to compute, a fit for a power law. So we did that in a previous chapter. So here we're getting the value, 2.38, 39, which we compare to the expected value or the theoretical value of 2.5. So again, we're not exactly, but pretty close to what we expect. And I mentioned already for the degree correlation. So there's, if you consider the directed graph or the directionality of your graph, sorry, then you can consider four different combination for the modes that we're going to use for the source and target node. But if we consider like out degree for the source node and in degree for the target node, then you can plot this degree correlation function, and you can vary and plot the other three, which are also included in the book. Okay, so next we're going to be looking at a model that allows to generate graphs that do have assortativity, negative or positive assortativity, this XBS algorithm. Okay, so it's parameterized by the main parameters are Q, which defines the amount of assortativity, and then is the assortativity positive or negative. Okay, so once again, there's more details in the book. But what we're going to do basically is we're going to fix the number of nodes and the number of repeats per set of parameters. And we're going to go through, this is kind of the important part here, we're going to go through 5 different combinations. So true means that we have positive assortativity, and false means that we have disassortativity or negative assortativity, and those are the value. So basically the first combination is going to be strong positive assortativity, then positive, neutral, then negative assortativity, and strong negative assortativity. Those are just some plotting parameters. So what we're doing basically is to go through our parameters and do a number of repeats, generate the graph, and compute the degree. Oh, that takes a while, so let's run this. Yeah. So here we go. So we're computing the degree, and we're computing the degree correlation function. So that's the average degree of the neighboring nodes for a node of for nodes of a given degree. And you can see in the case of assortative graph, you have your positive slope here. For disassortative graph, 1/3 or 2/3, you have those negative slope. And for neutral graph, you have essentially, zero, slope of zero. Okay. The graph is a little nicer if you take, larger value for n and a larger number of repeats, but this function can be slow. So for the book, we've used a faster version of this code coded up in the Julia notebook. And the in this one of the effect of assortativity is that having a positively or negatively assortative graph can affect the way that information is spread, right? So, for example, if you have strong positive assortativity, it could be the case that information will spread faster because you will build like a backbone sub network of your graph very, very quickly with the high degree nodes. So again, there's a discussion in the book, but this is illustrating the size, how the giant component grows, what fraction of node, so the order of the graph, what fraction of node are included in the giant component for different level of assortativity. So what we're doing basically is that for our range of parameters, we are looking at the size of the giant component divided by the total number of nodes and basically storing the result. And this gives us the result presented in figure 4.8 in the book.